Hello guys, welcome back. These are some of the requested questions by my student. Right, I know that Wednesday is your exam. Right, so I would like to take this opportunity again to wish you best of luck in your exam. So before that, let me try to answer some of your requests here. All right, now this is a questions by Ziyi. All right, is regarding the center of mass. Right. Now, this question was extracted from, if I'm not mistaken, is um, November 2020, paper 32, right? I'll try to include that in the description. You can check that out. All right, let's read through this. An object consists of a uniform solid circular cone of vertical height 4r and a radius 3r and a uniform solid cylinder of height 4r and radius 3r. That sounds like a lot of information there. The circular base of the cone and one of the circular faces of the cylinder are joined together so that they coincide. The cone and the cylinder are made of the same material. Now, by saying that they are made of the same material, it means that they should have the same density, right? So they should have the same density for those students who are studying science. So that actually refer to the same density here. We can call that uh, phi here, right? Now, in order to help you to illustrate how the shape actually look like, I have already prepared the drawing over here. You can see that it consists of a cone. The height is 4r here. Okay, 4r. And then it has a radius of 3r over here. Right. And then the height of the cylinder is also 4r. Right. And then now there's a bit of geometry that you need to pay attention to, especially when you handle the center of mass question or rigid body of a three-dimensional object. Now, for instance, in this case, we have 3r, 4r. We should know that the slanted length here should be 5r here. I'm just writing it down in case we need it at our later stage, right? So always pay attention to the geometry before we apply the mechanics itself, right? So I hope that is helpful. Now at this point, you are going to check out whether you have actually included all the informations provided in the text into that diagram itself, so that we don't miss out anything. Okay, after checking through, yes, we have already included everything. Knowing that both of these solid actually made up of the same material, they should have the same density here. Now, our first task is to find out the distance of the center of mass of the object from the end of the cylinder that is not attached to the cone. Now, basically, they are saying that this one will be our reference to where we measure the center of mass. So the center of mass is measured from this line here. So I'm going to put that down as a reference line. Okay. All right. Now, before we start to work out the center of mass, it's always best to construct a table to include all the individual objects that we combine together to produce that composite rigid body. All right. So here we're going to write down the solid. So what are the solids that we have? We have first of all the cone. Okay, we do have the cylinder, so we're gonna write it down here. And then finally we have the combined object, or here I just call it as a composite object or composite solids. All right. And then next, what are we interested to calculate here? Of course, because they both share the same density, you can include the density, or if you don't want to include the density, it also can. The main reason is because this density will be cancelled from the equations later on, right? So I'm going to show it to you in a while. I'm going to include the volume here because it's a solid anyway. Now the volume of a cone is 1/3 pi r. The r is 3r square, and then multiply by the height is 4r here. And then that can be simplified to, if you work that out, that will be 12 pi 12 pi r cube. All right. And then for the cylinder, it's quite easy. It's just pi 3r square multiplied by the height, which is 4r here. And then that will give you like a 36 pi r cube. All right, so just let me check through in case I miss out any symbol or variable here. Okay, I think I'm good. And then the combined solids or the composite solids, we just need to add up their volumes here. We have 48 pi r cubed there. There should not be any problem here. All right. And then next, we are interested in the center of mass. All right. Now this is I put down as a short form center of mass uh, from the reference line. From the reference line. So it's always best to remind yourself where do you measure the center of mass from. So we measure the center of mass from the reference line that I have highlighted here, right? So for cone itself, if you can't remember, you should always refer to the data booklet MF19. Now, according to the data booklet, the center of mass of a cone is located at 3/4 from the vertex. This is the vertex itself. I'm going to label that as like, yeah, maybe V itself. So this is where it is measured from. Okay, 3/4 of that. But our center of mass is measured from the reference here. Now, if you take 3/4 of this, 3/4 of the length here, you will notice that the center of mass is located somewhere here, which is 3r. With respect to, oops, sorry, with respect to the vertex, I think I draw it properly here. With respect to the vertex here, all right. Let me clean this up a bit. Right? So the 3r is measured with respect to the vertex is 3r. But we are measuring the center of mass from the reference line. Therefore, this is 4r plus another r here. That will give us, let me see, this is 3r. This is r. Yeah, correct. So that will give us a 5r with reference, with respect to the reference line up to here. This is where the center of mass for the cone is located. Right? Therefore, we're going to write this one down as 5r. So I hope that is clear. Next, for cylinder, cylinder is very obvious. It's just at the middle of the cylinder itself, which is 2r, measured from the reference line. Right? So that is just 2r. And then the combined center of mass, we can just label it anything you like. For instance, you just put it as x bar here. All right, and then basically we are done with the setup. Next, we just need to apply the principle of moment. Principle of moment state that the sum of the moment, or you can say that the composite moment, the moment of the composite solid is the same as the sum of each of the individual solids that build up that composite solids. All right. So how does that actually look like? It basically looks something like this. We have 48 pi r cube. This is the moment of the composite solid. Moment of composite solid is basically the um, the weight. Based on the original definition, is supposed to be the weight of the composite solid. Okay, so the weight is actually given by the volume multiplied by the density. You have the mass here actually, and then you multiply by the g to get the weight. And then after that, we're going to multiply that with the center of mass. Right. Now that is the moment of the composite solid. And then it is the same as the sum of each of the individual solids that build these composite solids. And then that would give us 12 pi r cubed. That's the volume. Multiply with the same density because they are made out of the same material, with the g to produce the weight, and then the center of mass of this cone with respect to the reference line is 5r. And then we're going to proceed on with the same procedure for cylinder. We have 36 pi r cubed, and then multiply by the density, gravity, and 2r here. And then there you have it. That is the principle of moment that we're going to solve shortly. So from here, you notice that the density and the gravity can be cancelled out. And then the pi r cube can also be removed. And then all we have is 48 x bar. And then here we have like a 60. I think it's a 60. Let me see. Yep. So it's just 60r here plus next one we have a 72r. And then of course at this point you can try to simplify it. For instance, you can simplify with, I think you can simplify with 12, right? 12 for instance, right? Now take for instance the one that I can see maybe is 12. So I'm going to divide everything by 12, and then that will be 4x bar, and this one will be 5r. And then if you divide by 12, it will be 6 here. Of course, these two you can combine them as 11r. Therefore, the center of mass of this solid, composite solid, is located at 11 over 4r. 11 over 4r is around 2 point something r there. Okay, that is like 2 point something should be located somewhere here. Right? Because 2 is around here, therefore the 2 in this case 11 over 4r should be located somewhere here, and then this is where the center of mass for the entire composite body or composite solid is located. So I can label that as, if you like, you can label this as G. Yep. And then there you go, that is the center of mass for the composite body. All right, I hope that is clear. I'm going to move on to the next one directly from here. Okay, if you are clear with this. All right. Now the next part, B, we need to show that the object can rest in equilibrium with the curved surface of the cone is in contact with the horizontal surface. Now I have already put it in that positions that can be represented by this question here. So the slanted or the curve section that is in contact with the horizontal surface. This is how it look like, right? Okay. Now I'm going to clean up the dimensions label here so that it's much more clearer for us to go through the explanations for number 2 here. Our reference line is still there. Okay. Right, and then we have already determined our center of mass with respect to the reference line that's located somewhere here. Okay, and then now the requirement for this solid to be able to stay in equilibrium at this position is this, right? Now you need to make sure that the line of the line of the weight must not exceed the pivot here. All right. So what I mean by that is the line of action or the line of the weight itself. So the weight is acting at the center of mass. So the weight should be somewhere here. I have no idea whether it will exceed this or not. This is just my assumption looking at my calculation just now. So this is the weight of the composite solid. All right, so I'm going to label that as W as the weight itself. Okay, or W in this case. All right. Now, the main reason why the line of weight should not exceed this pivot here is because if it exceed this pivot, okay, take for instance, I'm going to show it to you anyway here. Take for instance, if we had gotten a G differently, maybe it's below 2R for instance, then the line of the weight would be this one look like exactly on the line. I might want to make it more dramatic in this case. So the line of action should be acting somewhere like this. Okay, so this is the line of weight, and then we know that when the solid is placed in such a position, the maximum positions of the reaction force will be somewhere here. This is where the reaction is located. Now, if you take the moment about this pivot here, if we take the moment about this pivot, therefore, this weight would cause a turning effect clockwise. You can see that this is the only force that is acting with respect to the pivot here that will cause a turning force clockwise. Therefore, this particular composite body, right, would actually tilt or rotate clockwise then. Therefore, it can't stay in equilibrium. So because of that, we want to make sure that the line of weight would not be greater than the pivot itself. Hopefully it will look something like this. Hopefully the line of action should be somewhere before the pivot. That is the best scenario. So that if the reaction force, assuming that the reaction force is here again, now would the weight still cause a turning effect? Yes, of course, it will still cause a turning effect here. You can see that there is a moment about the pivot P here that is caused by the weight. But in any way, this turning effect would rotate counterclockwise. But because this all this area was in contact with the surface, so no matter how the cone is going to rotate counterclockwise, it will still stay on the surface unless unless this weight is just super huge, then it may actually sink into the horizontal surface, right? But of course, there's a worst case scenario. We assume the theoretical conditions whereby it will not sink into the horizontal position. So this turning effect will not turn this object into a condition that it would actually sink, right? Now, that is the conditions that we want to achieve. What I'm trying to say here is we want to make sure that the line of weight must be acting within this contact here. If this line of weight that is exceeded this pivot, it will cause a turning effect that will rotate in the opposite direction. That will cause the object become not in equilibrium, right? So I hope that is clear at this point. The conditions that you want to make sure that the object will stay in equilibrium is to make sure that the turning effect will not cause the object to become not in equilibrium, right? So that's the best conditions here. How are we going to check whether this line of action actually fall before or within this pivot here? All right, now we're going to check that. To do that, we can do this. Okay. Now, we have no idea whether this particular center of mass would actually provide a line of action that will be exceeding this pivot here. Therefore, we have to check at this point. The best way to check is we know that this distance here, since this is 11 over 4r, therefore this distance here to the vertex, this distance to the vertex, you can check. Alright, this distance is basically 8r because the entire height of the composite solid is 8r. So therefore, you can actually take 8r, subtract off with this 11 over 4. This will be 8r minus of 11 over 4r. That will be the distance from the vertex to the center of mass at this point. Okay. Now that would actually give us, let me see, this is 32, so 32, 21 over 4r, 21 over 4r at this point. Okay, and then we're going to use this measurement here, the vertex here until the center of mass, to determine whether this distance here, this distance x here, I think I prefer to use y instead. The x will be a bit confusing here. To determine the distance y, whether it would actually be longer than the length of the slanted section here, the curve section. Would it be greater than the length of the curve section? That's what we want to check. And then we know that the curve section VP, this curve section BP, the length of the BP is basically 5r. We have already determined that from the Pythagoras theorem. That shouldn't be any problem. All right. And then from here, we're going to check our y. How do we check that? We can apply a bit of trigonometry ratio here. So I'm going to remove this. Now, by looking at this, I'm going to redraw this so that you can see it clearly. I'm going to draw that right-angled triangle. All right. Now you know that this is 4r just now. This is 3r. Okay. Just to convince you that this is 5r, you can see that from the right-angled triangle, this is particularly 5r. That is the length from the V to P here. Right. Now our task is to determine the length y. If the length y exceeds 5r, therefore this line of weight must be outside of the pivot. Then it will not be in equilibrium. Right. Now to do that, we can apply trigonometry ratio here. All right. Now that should not be any problem. You can label this as theta, for instance. This theta here, this theta particularly, you can use any ratio that is relevant to the theta. For instance, in my case, most probably I'm going to use like cos. I would say that cos theta, based on that right-angled triangle, my cos theta would be 4 over 5. Now I hope that is clear based on this triangle here. All right. Okay, now we're going to look at the other triangle, BGW. BGW here. This triangle here, BGW. Now, based on this triangle here, we can take like a trigonometry ratio. We'll say that y, in order to measure or calculate the length for y, we can take 4r cosine theta. 4r cosine theta, that will give us the length for y. And then we know that the cosine theta is 4 over 5. So therefore, this one will be 4r by 4 over 5. And then that will give us 16 over 5 r here. Now 16 over 5 r is basically 3.2 r. 3.2 r. And then we know that 3.2 r is basically less than 5 r here. Therefore, this line of weight is within that pivot. You can say that it's to the left of the pivot. Therefore, this turning effect will not disrupt the equilibrium conditions of this composite solid. All right. Now I hope that is clear at this point. You can see that for the last section, there's a lot of considerations on the geometry, trigonometry. All right. So do pay attention to your trigonometry ratio, and then observe the geometry um, of the solid itself. All right. So I hope that is clear. Hopefully, so you can understand this. All right. And then the rest who are watching, I hope that that is clear. All right. Now, next, I'm going to move on to another question that is requested by another student, Jen, if I'm not mistaken. Jen, Jen Deaver or Jen. I can't remember the Jen Dizer, I think, right? Please forgive me if I pronounce your username wrongly. Okay. Now I'm going to proceed on to the next question shortly. All right, welcome back. These two questions was from um, year 2020, paper 33, requested by Jen Dizer. All right, thanks for your support here. Hopefully you will do well in your upcoming exam. Right, now I'll try my best to explain this as clear as possible. All right, so I hope that will be helpful to you. Okay. Now, here we are looking at the two smooth sphere A and B have equal radius and masses of m and 2m respectively. Okay. Sphere B is at rest on a smooth horizontal floor. Sphere A is moving on the floor with velocity u and collide directly with B. The coefficients of restitutions between the spheres is E. We need to find A in terms of u and E, the velocity of A and B after collision. Velocity of A and B after collision, right? So it's always best we're going to draw out the diagram to show how does it look like. So here I'm going to draw out a very simple diagram. We can see that very clearly. Right. Now we can see that it is A. So we have a particle A here. That is moving at the speed, what's the speed again? U. And then there's another particle that is B here that's at rest. All right. Now we know that the mass for A is m, and then the mass for B is 2m respectively. The coefficient of restitutions is E. Now here I just highlight that coefficients of restitution. Okay. All right. Now there are two things we need to remember when it comes to um, question related to momentum or collision, right? That is conservations of momentum. Conservation of momentum state that the total momentum of an isolated system would remain constant. By that, it means the total momentum before collision must be the same as the total momentum after collision. So we're going to apply that first, right? Using conservations of momentum. Total momentum before it's just this one. M is the only object that is moving. Particle A or sphere A is the only object that is moving. So we have a total momentum before collision is given by mu here. And then this is before. I might want to label this as before. And then after. Right. Now after, I'm going to put it down here. It's easier to see. After. Right now, after, logically speaking, most probably A will still proceed on in the same direction. Here I just label that A could be moving in this direction, in the same direction, but with a different speed. This is A, right? And then B, of course, after receive extra momentum, for sure is going to move in this direction. I will label that as BB. It also have the same mass. Let's assume that the mass never change. Right. Now that is how it looked like after the collision. Therefore, from here, we know that the total momentum before collision is mu. The total momentum after collision is given by mva plus 2mbb here. Now the other thing that most of us would be wondering, like, um, should we consider the directions where they could be moving? Could could A be bouncing back or not? And so on. Should I think about negative sign, positive sign at this point? So usually for collision after collision, usually you don't really need to pay too much attention to the direction, because we we have no idea whether it's going to rebound or whether it's going to move in the same direction. It's just that logically speaking, we do assume that it should be moving in the same direction there, right? So therefore, I would like to stress that don't pay too much attention to the sign itself. The math itself, the equation itself, will synchronize the sign later. All right. So I hope that's helpful. From here, it's always best to simplify as much as possible. Any factor that you can simplify, simplify it, right? Or else it's going to be a mess. And then there you have it. That's our first equation. We can't do much at this point. Now, in order to solve for the the velocity of A and B after collisions, we need another principle, which is introduced by Newton. This is called the Newton restitution law. So Newton restitution law, I put it in short. Now, Newton restitution law state that based on the symbol here, we can write it down as the coefficient of restitution is given by this ratio. Okay. Now for me, I always take the positive value. I always take the BB minus BA and then divided by the opposite difference. So if I start off from BB, I should take the UA instead. So UA minus UB, because the initial velocity of B is 0. Therefore, this is where the 0 come in. All right. But then again, some students may prefer to do it this way. They prefer to do it BA minus BB is equal to UA minus UB equal to negative E. You can also use that. That would be the original formula for Newton restitution law here. But for me, um, I don't really prefer negative sign here. So therefore, I purposely readjust the restitution law to meet my requirement here, right? So if you like that, you can use it, right? Okay. For this time being, I'll just stick to my preference here, and then from here we can rearrange this so that we get this equation. Okay. Now most of the time, we prefer to write as EU or UE. Doesn't matter. It's just a symbol. All right. Now this is our second equation. And then our intention is to find out the velocity of A and B after the collision, which are our BA and BB. To get that is a piece of cheesecake. You can see that. We just need to solve this equation 1 and 2. All right, now we're going to solve it at the side here. Doesn't matter how you like to solve it in this case. I think I accidentally wrote this one down wrongly. You can see BB minus BB. BB minus BB definitely is going to be 0. So this one is BA. So, right? So I make a correction here. All you need to do is just take 1 with 2, and then the BA can be cancelled off. We have 3BB is equal to 1 plus EU here. Therefore, we conclude that the speed of V, or you can say velocity, here doesn't really matter because the object is just moving in one direction. That will be 1 plus EU. And then there you have. There you go, right? And then next, all you need to do is just substitute into number 2, for instance. We can, from equation 2, we notice that BA is BB subtract off with EU. And then you can take this, put it into here. That is this, subtract off with EU. And then once you simplify that, you will notice that that is actually 1 minus 2e over 3u. And then there you have it, the velocities of A and B after the collision. All right, now I hope that is clear. I'd like to stress again, always draw the diagram before after to let you visualize before you proceed on with the algebra. Right, so I hope that's clear. I'm going to pause here for a while, and then later on I'm going to move on to the second section. All right, the second section, we are still on the same question 6 here. Subsequently, starting from here, subsequently, after the collision, B collides with the fixed vertical wall, which makes an angle theta to the directions of the motion of B, where the tangent theta is given as 3/4. The coefficient of restitutions between B and the wall is 2/3. Immediately after B collides with the wall, the kinetic energy of A is 5/32 times the kinetic energy of B. Therefore, we need to find out what are the possible values of um, coefficient of restitutions here. Now, the same thing, we are going to redraw again. This is from a different perspective now. Okay. Now, we know that after the collision, okay, I would say that from here, maybe I draw it this way. Okay, this is particle A. Particle A previously was moving at after collision. I'm talking about after the first collision, it is moving at VA, which is given by let me see whether I remember this correctly or not. Let me see. First of all, yes, so it's 1 minus 2e over 3u. Okay, and then the B itself will be moving in this direction, for instance, all the way up to here. Let me clean this up here, all the way up to here until it collide with the wall. Its velocity before it collide with the wall is BB, which is given by 1 plus E over 3E here. And then the wall is over here, is making an angle theta to the directions of the motion of B here. This is wall. All right. And then for sure it's going to bounces off from here for B itself. And then most probably it's going to make some angle at this point. It will have a certain speed here. I'll just label it as WB itself. This is how it looked like from that perspective after collision. All right. So I hope that is clear. I think I'm going to transfer the BA over this side so that we can just use it as a reference rather than putting it there. And then BB is 1 plus E. Okay, and then there you have it. We don't need this anymore. Okay, now those are the informations that we have. Now from here, the collisions with the fixed vertical wall, here we don't actually apply conservation of energy. For those students who are taking physics, you will know that why we can't apply conservation of energy due to present or external force, which is gravity here. Right now, therefore, for collision with a fixed wall, we can consider the component of the velocity. So we know that the only component of the velocity that has impact with the wall is the vertical component. Okay? That is the vertical component or the component that is parallel to the normal itself. Right? The component of the velocity that is parallel to the wall will not have changes. Therefore, we conclude that here the W cos alpha, which is the horizontal component of the velocity of B after collided with the wall would stay the same as the horizontal component of the particle or sphere B when it collide with the wall itself. That will be BB cosine theta. And then there you have it. That is something like our first equation. Right? We can't do much here, except of course we do have the three quarter there. Right? You can always substitute that. Okay. Now the other thing that might change due to the direct impact with the wall is the vertical component of the velocity itself. So the vertical component, we will have to make use of the restitution law. Now for that, we know that the W B sine component of the velocity will be all right. Now if I were to actually use that um, Newton restitution's law here, Newton restitution's law, it would actually look something like this. Now, because the wall is not moving, before collision is zero, after collision is also zero there. So I can actually use this as my reference. I can say that um, how would I do that? Let me see. WB sine alpha minus of zero divided by the initial velocity here, which is BB sine theta. Oops, sorry. Yeah, you can do it this way. Minus of 0 is equal to 2 over 3 here. Now, bear in mind, the actual formula, based on what I explained previously, is supposed to be 0 because if you take the B component first, then your denominator, you should use the wall first, then following by your vertical component of your velocity after the impact. Now that will be WB. Oh, sorry, this is the initial before impact with the wall itself, which is BB sine theta. From here, right, you will notice that there is a negative sign there. So we notice that WB sine alpha equal to negative 2 over 3 BB sine alpha. There is nothing wrong actually, but most of the time the textbook don't really tends to write the negative because negative just signify that it's moving in the opposite direction. But if you do want to include that, by all means, you can always include that here. Right now, from here, we are interested to get the speed of the B after the impact with the wall itself. So therefore, we are interested to solve this simultaneous equation, basically. Right now, we are not interested in the direction, so we can leave the alpha out at this point. To solve this, for me, I would tend to apply the trigonometry identity, 1 square plus 2 square, so that I can get rid of the sine square here. I will get WB square. Alright, now inside there is basically just sine square alpha plus cos square alpha. I think most of you know this identity. That will be the same as the is this b square? Let me see. Oh yeah, this is b square. So b square cosine square plus, you will notice that the negative doesn't really affect much of our calculation. 4 over 9 b square sine square. And then that will be WB square is equal to all this calculation here. And then we can substitute all these informations in. We will have BB. Our BB is over here. It's a square. And then cosine square. Right. We know that tangent square is 3 over 4. If you were to draw a right-angled triangle here, for instance, if this is theta, 3 over 4 right-angled triangle, therefore this one must be 5. Tangent theta is equal to 3 over 4. Therefore, cosine theta must be equal to 4 over 5. And then sine theta must be equal to 3 over 5. We're going to use this standard ratio to answer this one here. We have cosine theta, which is, in this case, is 16 over 25. Right. And then we have 4 over 9. The b square, bb square is the same thing here. We have 1 plus e over 3 square, and then sine square, which is 9 over 25. All we need to do is just sort of simplify all this. Let me see. I think I left out my u square. Yeah. Okay. I'm going to leave that out. Now from here, you can see that I would have, okay, basically the 9 can be cancelled off, and then I will have a 4 over 25 and 16 over 25, which basically give me 20 over 25, 1 plus e 3 square u square. And then therefore, my speed b after colliding with the wall is given by the square root of this. Right? So the square root of this, that will be like, let me see here, 2 5, 2 sub 5 over, this one will be like 515, 1 plus e u here. Now that will be the speed of b after the collision. Right, now I'm going to pause here for a while. I hope that is clear. At this point, we have successfully obtained the speed of b after colliding with the wall. Now we're going to analyze its kinetic energy, and then by doing so, we should be able to work out all the possible value for e. All right, so I'm going to pause here for a while. We're going to proceed on shortly. All right, let's continue on with the next section here. We have previously found out the speed of b after it collide with the wall, which is given by this value here. Right. Now next we're going to make use of this information where it's stated that the kinetic energy of A is equal to 5 over 32 times the kinetic energy of B after B collide with the wall itself. Alright, so we're going to use that, and then we know that the mass of A is m, the mass for B is 2m here. It says that the kinetic energy of A is 5 over 32 times of kinetic energy of B here. Now the kinetic energy of A is very straightforward. It's just half m VA square, and then we know that our VA is over here. Okay, now that will be our kinetic energy for A, and then next we have our kinetic energy for B, which is half multiplied by 2m, and then the speed of B after the collision. Then that will be, if you square that, okay, I'm going to put that in originally before square. Okay, now there you go. And then of course we can slowly simplify this. We can remove all the u square and the m, and then here we have like 18, 1 over 18, 1 minus 2e square, and then what we have here would be, let me see, we have 5 over 32 first, and then if we square this one here, we have a 4, I think it's a 4, alright, and then after that you have like 5, 3, 45, okay, 1 plus e squared. I hope that's clear, right? So from here we're going to further simplify this. We have like this part will be 1 over, let me see here, 9, 8, 72. So 72, 1 plus e square. And then we can simplify all this. We will have 4, 1 minus 2e square is equal to 1 plus e square here. Now, of course, there are many ways to do this. You can either expand everything, or I noticed that this is a 2, so you can take square root both sides. Okay, when you take square root both sides, there is always that plus or minus that you need to pay attention to. So take for instance, if I take a square root, it will be plus or minus. I'm going to consider my first case whereby it is plus. Okay, and then from here, I'm going to solve that. I found that um, my my 5e, I'm going to move over. 5e is equal to 1. Therefore, e is equal to 0.2. That's my first case. Then for my second case, I have to consider the negative of it, right? So the negative will be 2 uh, negative 1 minus 2e is equal to 1 plus e here. And then all I need to do is just solve this. I will get like a 3e instead. I think I get my 3e. This is 4 by 1 is, and then after that, on the other side, I have 3 also. Therefore, second possible value for e is equal to 1. All right, now I'm going to pause here. There are many ways to solve this quadratic equation, of course. The more direct way is just to expand everything, right? Or else you can just take square root. But don't forget, when you take square root, don't forget the plus or minus, or else we will be very rude in this case, right? So I hope this question is clear. I'm going to move on to the second questions raised by Jen Dizer, right? Hopefully that is helpful. Okay, I'm going to move on shortly. All right, welcome to another question raised by Jen Dizer. Now, this is the same paper, paper 2020, paper 33, question 7 here. All right. Now, a particle P moving in a straight line has displacement x from a fixed point O on the line at time t second. The acceleration p in meter per second square is given by this expression where the x has to be greater than 0. When t is equal to 0, the initial displacement is 1 meter, 1 unit, yeah, 1 meter anyway, and p has a velocity of 10 meter per second directed towards O. The first question is we need to show that the velocity v or p is given by such. Then secondly, we need to show that as the x and t are connected in such a way. And then finally, we need to deduce that in the long run, as time progresses into the future, what will happen to the displacement is. All right, let's get started here. The first one, we have been given the acceleration. Of course, most of you would straight away jump onto the algebra and so on. But my suggestion is always draw out a diagram just to visualize in case we miss out any detail that we are supposed to look at. So take for instance, this is our reference O here. Now at the initial position, initial condition here, t equals 0, the particle is located at 1 meter from the reference point, which is our fixed point here. Now therefore, the particle is supposed to be here. This is particle P is located at 1 meter. All right, this is how it looks like. Right? And then it also says that initially the particle is moving at the speed of 10 meter per second directed towards O. So that is directed. You can see that directed towards O. Now this direction here, based on the mathematical time, the frame that we are using here, we assume that moving to the left is negative, right? So negative here, right? So therefore, we are going to label the velocity as negative 10 meter per second here. Now I hope that's clear. If it's directed towards the left hand side, we assume the velocity should be negative. Or in this case, we assign the direction as negative. Okay, let's check out the rest if we have already fulfilled all the property that is given for this linear motion. Let's check. We have the 1 meter. We know that initially at the start, it starts from here at t equals 0 second. It started to move to the left towards the O. Okay, and then the acceleration of this particle is given by this. Now there are many versions of the acceleration. It could be rate of change in velocity, okay, which is given by dv dx by dx dt. And then we know that dx dt is velocity. Therefore, we can change the accelerations formula as v, this part is v, dv dx. You must be wondering, why am I doing so? I'm doing so because I need to find out the connections, the relations between the velocity and the displacement. Therefore, I can't use time here. For this equation, there is no time involved. Therefore, using dv dt may not yield the result that I want. Right? That's why I have chosen v dv dx here. This is given as 200 x squared minus 100 x cubed. Okay, the rest after this is just merely performing an antiderivative to find the relations between the velocity and the displacement. Now, divide and conquer. We're going to group all the like terms to one side. Like this. And then thereafter, we're going to perform the antiderivative like this. All right. And then don't forget, be very mindful when you do integration. Integrations is increasing the index. That's where the I actually come in. Integrate means increase. This is a reminder. And then next, this one also you have to be very mindful also is negative 200 over x and then plus 50 over x squared. Plus a c, don't forget that piece of cheesecake there or completion. Now, once you are here, we're going to make use of the initial condition. At time t equals 0, its initial displacement from the origin is 1 meter. And then velocity is negative 10. All I need to do is just substitute all this. One plus a c. And then from here is pretty obvious that we have the c equal to 200. You can check that out, it's very obvious. And then from here, we are going to conclude our relations between velocity and displacement. That is v squared over 2, as indicated here, is equal to negative 200 over x plus 50 over x squared plus 200 here. Now that's what we have currently. And then from here, all we need to do is try our best to factorize it if we can. So one way to do it is maybe we can multiply everything by 2. Okay, multiply by 2 and then factorize out the x squared. So, therefore, I'm going to take out the x squared here. If I take out the x squared, I will have, after I multiply by 2, I will have my 400 x squared minus of 400 x, and then finally I will have to include the 50. Oops, I forgot to multiply by 2. It should be 100. Let me correct that. Okay, and then I notice that all this can be factorized out. So you can take 100 over x squared. Then that will be 4x squared minus 4x plus 1. And then that could be factorized quite easily. That is 2x minus 1 squared. And then you notice that all these can be square rooted quite easily. Then we can conclude that the v is equal to plus or minus. Yeah, again, don't forget, it's very rude not to include the plus or minus at this point. So it has to be plus or minus. I shouldn't have concluded this yet. I just say that when you obtain the relation between velocity and the displacement, there's always a plus or minus because we square root this, become 10 over x, 2x minus 1 square. Sorry, there's no square anymore. All right. Now this is the difficulty here at this point, right? We can't afford to have a relation because this velocity is supposed to be a function. You cannot have plus or minus. Therefore, where does the plus or minus that we are supposed to select? This is where this come in. The velocity at the initial condition is negative. So you can check when x is equal to 0. When x is equal to 0, sorry, not x equal to 0. Initially, when x is equal to 1, we're going to substitute this one here. If you substitute x equal to 1 into here, you will get positive 10. We get a positive 10. But we do know that the direction of the velocity is pointing towards O. It's supposed to be a sign negative. Now, because of that, we will have to choose the negative direction for this velocity. Because when you substitute x equal to 1, you are supposed to get a negative there. Now, due to that logic, we conclude that, in this case, I'm going to draw a line here. So we conclude that v must be equal to negative 10 over x 2x minus 1. Or you can write as 10 over x 1 minus 2x here. And then there you have it. That will be the velocity functions that is written with respect to displacement. Okay, so I hope the negative sign is clear to you, right? Now next, we're going to answer that second part directly from here. I'm going to erase off all this section at this point. We don't need this anymore. Okay, we don't need this anymore. And then we have obtained the equations that we need, which is v equal to 10 1 minus 2x over x here. Okay, it has been proven here, right? Okay. Now what we need to do now is to show the relations between the displacement and the time itself. Okay, this is where the relations between the velocity and displacement come in. Velocity is defined as rate of change in displacement. Therefore, you can, okay, I think it's better I write it down over here. It's given as dx dt. Now from here, we are going to perform another round of antiderivative so that we can obtain the relations between displacement and time itself. Now, by performing the same divide and conquer or grouping your like terms, in this case, all the x will be grouped onto one side, t will be onto one side. Okay, so now that would actually be x over 10, 1 minus 2x dx is equal to dt. Now that's how it look like. If you like, you can also write it down as such. So take for instance, you can bring the 10 over if you want. So that is 10 dt is equal to x over 1 minus 2x dx. And then thereafter, we're going to perform the antiderivative. Okay. So I hope that is clear. Now getting the first part of the integration is a piece of cheesecake. It's just 10t. That shouldn't be a problem. So here I'm going to rewrite that as 10t equal to x 1 minus 2x dx. Alright. Now you still remember, in order to integrate this, you have to apply partial fraction. But bear in mind, before you apply partial fraction, you must check the degree of the numerator and the denominator. If they are the same or higher, if the degree of the numerator is the same or higher than the degree of the denominator, it's best to perform a long polynomial division before obtaining the partial fraction. So this is how we do it systematically. Of course, there's a very creative way of rearranging this to get the partial fraction. But if you don't want to follow that, you can always use this systematic way of obtaining the partial fraction using long polynomial division. Anyway, it's not that long. Now I'm going to perform the long polynomial divisions over here. Long polynomial division, LPD. Okay, now by taking this divided by this, so one way to do it is I have to multiply by negative half. that will give me an x minus half. Therefore, from here, for this part here, I can write down x over 1 minus 2x in its partial fraction form, which is given as, all right, there you have it. You can always check by combining this, it should yield the same result. Therefore, integrating this is the same as integrating this. Okay, and then there you have it. And then all we need to do is just go through the same integrations procedure. We will have 10t equal to, shouldn't be a problem, that is just a negative half x. And then this part you have to be very careful, is actually 1 over 1/4 because of this negative half, and then the entire thing become ln 1 minus 2x. And then I also need to remind yourself that whenever we handle logarithmic, it cannot be negative. In order to prevent any chaos happening to this logarithmic function, it's always best to put an absolute sign so that the negative conditions will be treated as positive in this case. And then don't forget, plus that piece of cheesecake. All right, and then there you have it. At this point, all we need to do is just utilize the initial conditions one more time. When t is equal to 0, x is equal to 1. So if I put this 1 here, I will use, this section will be 0. This one will be half, and then t is equal to 0. So therefore, c is actually equal to a half. And then I can rewrite this as 10t equal to negative half x negative quarter plus a half. Just let me recheck one more time in case I make a mistake over here. Let's see. Yes, and then there you have it. Now, in this case, I try to achieve this particular result. I notice that there is a negative 40. So I have 40t here. Because I want that negative 40, therefore, you may have to purposely introduce that into the equation. All right. Now, I'm going to erase all this small section here. We don't need this anymore. We're going to work out all this separately on this side. Okay, now before I do anything, I'm going to combine the numbers together. For instance, in this case, I can rewrite as half x minus 1 minus quarter. Now the usual case is to combine the non-logarithmic together, and then the logarithmic will separate them from the on group, right? So just to have a quick check, yes, we do agree on this. And then in order to achieve the negative 40t, I will have to multiply both sides by negative 4. If I multiply negative 4, I will have negative 40t, and then this part will be 2. It will become 2x minus 2 then. And then this part will be ln 1 minus 2x. There you have it. And then from here, all I need to do is just, well, you can apply the anti-log, right? So if you apply anti-log both sides, it will become negative 40t equal to anti-log 2x minus 2 plus ln 1 minus 2x. This is how it look like. And then, of course, index rule allow us to divide and conquer. We will have e2x minus 2 by e ln 1 minus 2x. And then that will yield 1 minus 2x e2x minus 2. And then just let me check whether I got it correct. Now, let me see here. So from the way I see it, I did not make it true. Just let me check if I did anything wrong here. multiply negative 4 over this side, so it should be 2x minus 2. Okay, so I do have my 2x minus 2, but somehow I'm not getting 2x minus 1. Where did the whole thing go wrong? Let me try to check one more time in this case. Right, so I have my negative there. Okay, that is correct. Then did I miss out anything here? Just let me have a quick check here. Supposed to be a negative in front. Mhm. Okay, I'm gonna pause here for a while. Just let me check for a while. If I take out negative, should be negative 1 there. Did I calculated my value wrongly? Let me see here. When this is a 1, this should be a 0, should be a 1, and then it should be a 0, it should be a half. Okay, there's nothing wrong. All this is good. So when I take the anti-log, should be here plus yep. So nothing wrong with this so far. I'm gonna pause here for right after checking through, right? There is nothing wrong at this point. Now you can see that starting from here, I do have exponential ln here, but because of the modulus sign, I could have positive or negative. The big questions now is, I think I miss out this part here. I should put a modulus here. The big question now is, should I be choosing a positive or should I be choosing a negative? That's the key thing, right? So students might be struggling at this particular point. Now, the thing that can help you is this part here. X has to be more than 0. So because X is more than 0, therefore, we don't really need to worry about this section here to be negative. So therefore 1 minus 2x would always be more than 0, given the value of x is always greater than 0. Okay, so if you choose 1 minus 2x for x that is greater than 0, then this value will be a negative. This value will be a negative. What I mean is this entire thing will be something like this. 1 minus, if you have chosen, if you have chosen this, now we know that exponential is always greater than 0. This would always be greater than 0. Then therefore, this one must be positive then. This one must be positive. In order to make sure that 1 minus 2x is positive, okay, we have to choose the negative sign from the modulus, or else this will become negative for x greater than 0. It can't be negative. If there's a negative, there is no real solution at this point. So I hope you guys can think about this and or organize your thought on this. This is a very good question to attempt on. Right? So because of trial and error here, I noticed that yes, it doesn't make sense. Therefore, I would choose the negative section of the modulus. And then I conclude that negative 4t is equal to negative 1 minus 2x exponential 2x minus 2. And then from here, I will notice that this will be 2x minus 1 exponential 2x minus 2. And then there you go. We have proven that relationship. And then finally is to deduce what happens to x as t become large. So here, this is quite direct at this point. All we need to do is, as x approach infinity, right? So as x approach infinity, right? So I'm running out of ink at this point. So as x approach infinity, what will happen to the exponential? You will notice that the exponential negative 40 would definitely approach 0 here. This one would definitely approach 0. Okay, this part would definitely approach 0, and then therefore because exponential 2x minus 2 cannot be equal to 0. So the only solutions that we can have at this point would be, okay, I'm going to pause for a while. I'm going to recharge my pen for a while. Let me rewrite the last solutions one more time. Okay, I'll try to clean this up so that it's more presentable. We know that from here, negative 40t is equal to 2x minus 1. And then that will be exponential 2x minus 2. Okay, so as t become very large, now we know that exponential negative 40t will approach 0, definitely. And then because of that, right, we know that 2x minus 1 exponential 2x minus 2 will approach 0. And then we know that this exponential will not be equal to 0. So the only time we can have 0 is when this expression here approaching 0. And then we know that x will approach half here. All right. Or you can write down in terms of limits in this case. So as we can write as in terms of limits. So limits as t approaches infinity. Okay, what will happen to this particular term? This term here, 2x minus 1 exponential 2x minus 2, this will approach a half here, right? So I hope that is clear at this point. So this is a very tricky questions. There's a very minor part that you need to pay attention to, right? Well done, Zendizer. Okay, so hopefully I pronounce your name correctly. Thank you very much for requesting these questions so that everyone can pick this up for the exam on Wednesday. All right. So thank you very much. And then if I have extra time, I'm going to produce another complete videos for the mechanics. If I don't have, then you guys will use this as your reference then. All right. So best of luck to all of you. Until I see you guys again.